Okay, cool. So hopefully you can see my screen and everything. Everything's recording. Let me go ahead and get started. So, yeah, this section is talking about exponential functions. And so exponential functions are new types of parent functions that we will need to remember. And so it says it in my notes. I have my notes right here to reference as well. But exponential functions, they have a domain of all real numbers. And they generally don't have any x-intercepts. And you can notice this from the first page of the notes on exponential functions. There's a graph I put at the bottom of that page, and there is an asymptote. There's a horizontal asymptote. Oops. The graph has no x-intercept. Okay, so no x-intercept is true. Okay. Yeah, so it does not have an x-intercept because there's an asymptote. There's a horizontal asymptote on the x-axis, which means without any transformations, there cannot be an x-intercept. So the fact that there's not an x-intercept is true. Okay. And the range is 0 to infinity because everything happens above that horizontal asymptote. So just conceptual things like that. I mean, those are pretty quick problems to get through, but those are crucial bits of information about what the graph itself is doing. And this is one of the problems. I didn't do this problem. I did a problem kind of similar. I did 18 and 19. So I'm going to go ahead and do this problem. So let's just have -1 and 1/8, 0 and 1, 1 and 8, 264, 3 and 512. And it wants us to determine whether this is an exponential, a linear, an exponential function, a linear function, or neither. The best way to determine that is by determining if this, so an exponential function always takes the form of its f of x is equal to a times b raised to the x. Or some similar form. In my notes, I put c times a raised to the x, or if you watched my video on me doing a similar problem, I may have called it something else, but it's just a number in the front, there's a base, and then there's an exponent. And so really to figure this out, we need to plug in the points, because what this gives us from the question, it's an x and a y value that this gives us. So each one, so it gives us 5 ordered pairs. So we can plug in these ordered pairs and see if we can figure out what a and b are. That is assuming this is in fact an exponential function. And I think one of the easier ones to look at is this ordered pair right here, because there's a 0. And what's nice about 0, so I'll do this in blue. So if these 5 ordered pairs represent an exponential function, then if we plug in 0, 1, then this will be 1 is equal to a times b raised to the 0 power. But b to the 0 power is just 1. So that's now just 1 is equal to a. And so we already figured out a just that quickly. So now what this comes down to is now our function that we had before is now f of x is equal to 1 times b raised to the x, or simply just b to the x, because the 1 doesn't really matter too much. And now we need to figure out what b is. And that's when I'm going to pick another point. In fact, I'll just pick this next point, the 1 and 8. So I'll pick that point as well, and I'll do that in blue as well. So 1 comma 8, that tells us that 1 is x, 8 is y. And so that tells us that 8 is equal to b raised to the first power. Or in other words, 8 is equal to b. And so we can just conclude now that the function is exponential, and it has the form of simply 8 to the x. Oops, not like that though. 8 raised to the x. And that's the answer. So we're slowly taking the generalized form over here. Yeah, we're taking this generalized form over here, and we're slowly trying to figure out what the constants have to be, what a and b represent here. We go through and we figure out that a is 1. So then we can plug in for a, and then we go in, we figure out that 8 is b, and then we can plug that in. And then we have our exponential function. Okay, yeah, you get the point though. It's kind of tough typing on this tablet thing. Okay, cool. So if you don't have any questions about that one. Oh, Shannon, I see you're in here now. Shannon, did you have any specific questions you wanted me to go over, or if you just want to see me work out problems I didn't talk about in the notes, that's perfectly fine. Okay, cool. I'll just keep going then. All right, so let's skip past that one. I did 18 for example 2 in the notes. I also did example 19 as well. So skip past those. And I also did number 20, or I did a problem just like number 20 for example 3, part 1. So I'm going to skip over that one as well. And I did this one for part 2 in the class notes. So I think the next problem might be something a little bit more unique. So I'll do 22 here. Let's see. Yeah, I'll do 22. Okay, cool. Okay, cool. So 22, it's giving us this graph, and it wants us to find the correct function, really by process of elimination. So what we can do is, or what we have been doing for these, is we look at the graph over here on the left and see how does it resemble our parent function. So remember the parent function, and I have this written down again in the notes. Yeah, there's a horizontal asymptote here. And then the exponential function does this with the y-intercept right here. And so we might already notice that the graph here already looks a lot like this. In fact, it might even be precisely the exponential function without any transformations whatsoever, because that's what really differentiates these problems from one another. So what I wrote down, albeit very poorly, but what I wrote down is the parent function for, so a times b raised to the x, or whatever variables are used. It all represents the same thing. So I don't see any transformations at all. I don't see any reflections. I don't see, to my knowledge, any shift of the graph. So I'm going to assume that there should not be. So 22 has no reflections. So what this means is no negatives. I shouldn't see any negative signs anywhere because that normally means a reflection of some kind. So if we were thinking about this in terms of process of elimination, there's A, B, and C, D, E, F, G, and H. Let's see. So that gets rid of B, and that gets rid of C as well. D is out. E is not technically a negative on the function. We'll get rid of it for other reasons. Right now, we're just getting rid of everything that has a reflection tied to it. G also has a reflection as well. And also H. H does have a reflection about the x-axis because the negative's in front of the 4 raised to the x. And so that's already a very great indication of, what we have to look at. And additionally, so what I'm imagining is that this is A because there's no shifting whatsoever. So I'm thinking that this is A. And then E, if you look to the left over there, that implies we're going down 1. And then for F, it's to the right 1. Now, technically, so it cannot be down 1 because if you go down 1, your horizontal asymptote goes down 1. But here, the asymptote is in my graph and on the graph provided, the horizontal asymptote is in the same spot. So it cannot be E because we definitively know that we are not shifting down 1. But technically, we can't immediately remove the idea that it goes to the right 1 because there's no asymptote. There's no vertical asymptote to reference. I mean, it looks like everything's unchanged, but there are certain problems that look pretty identical if you move to the right 1. Now, how often do those come up? That just depends on what kind of questions you get in the homework. So a quick way to determine it, whether F is correct or not. So what F says is that this is 4 raised to the x minus 1. And I want to pick a point from the graph. I'm going to pick a test point from the graph to just check. Let's see, one of the test points from the graph, it says if you plug in 0 for x, you get 1 for y. We can obviously plug this in and determine very quickly. So that test point of 0, 1, I get that from the graph itself on the stated problem. I see that, and I also do this in my lecture as well. I pick a test point to try to differentiate between 2 or more options. But I see 0, 1, so I can plug in 0 for x, 1 for y. So if you plug in 0 for x, you get 4 to the negative 1, which is 1 over 4. But we were supposed to get 1. So it can't be F. It has to be A. And so that's really the central thought process here. trying to use process of elimination via how the graph provided corresponds to the parent function, which goes back to the idea that this parent function right here, this is very important. This definitely needs to be known, especially because you will not have this information available on the final. So you need to know the information about this. And I do state it a little bit more compactly in my video. So that may be something worth referencing. Okay, so I'll go ahead and continue to another problem that I didn't cover from my video. I think I do want to also talk about 23 as well, because there's a reflection and a shift, which in my problem for example 3 part 1, it doesn't cover the shift aspect. So let's see if we can knock this one out right fast. Okay, so we have another situation here where just trying to figure out which graph is correct. And remember, this all compares to, sorry, these tablets are, they take a little bit of getting used to. Okay, there we go. So remember, the parent function is just like this. So how this parent function compares to the graph that's provided in the original problem, there is, and I'm going to start writing down these characteristics. There's obviously a reflection. And the reflection seems to be happening across the y-axis. Originally, it's going up like this, and now it's going down in the shape is reflected, in other words, across the y-axis. So across the y-axis, so remember that what that means is x is negative. So that's something to keep in mind. We will want a negative x. And it also, again, it may not look like it, but there's also a shift to the, there's also a shift going on here. In fact, we'll just go ahead and ignore the shift for now. We'll just use the reflection and narrow down this problem. So if we have the A, B, C, D, E, F, G, H, let's just get rid of these one by one. So what we have is the reflection that tells us the x has to be negative. A is out, B stays, C has the wrong reflection, D is okay, E doesn't have a negative on the x, F doesn't have a negative on the x, G does, and H does not. So just looking off of an x being negative, we are down to, let's see, we're down to 3 options. So we're down to B, D, and G. Okay. So we can try and determine characteristics about these 3 individually, or we can use test points to see if we can determine which one of these it has to be. So B only has a reflection about the x-axis, no other transformations. D has a reflection about the x and the y-axis. So I'm going to go ahead and already mark out D. Because D, if you notice on the left, D also has a negative sign in front of the whole function, which means that you would reflect about the y-axis as well, or the x-axis, sorry. You would reflect about the x-axis. So D has too many reflections. And G is actually a, well, it's a shift to the right one, which may be a little bit tough to see. But that's why I'm going to use a test point. So what B says is y is equal to 4 minus raised to the negative x, and what G says is y is equal to 4 to 1 minus x. And the test point we're going to use, one of the obvious points that I see is 0, 4 on the original graph that's stated in the problem. If you look closely, you will see that for an x of 0, it hits the y axis at 4. So if we try this for B, if you plug in 0 for x, 4 to the negative 0 is actually just 1. That's not 4. We were supposed to get 4. So B is automatically eliminated because it failed that one test point. In order for a function to be correct, it has to correspond to all the points on the graph. But if we pick option G, which says 4 to the 1 minus x, which x ends up being 0, that's just 4 to the first power, which is 4. So it's option G. And that's kind of the thought process. So I wanted to make sure everyone was okay with that, variety of transformations of the graph. So in this problem, it's answer G. Okay, that was worth a shot. Okay, cool. Okay, so I guess I'll go ahead and keep doing problems. So I'll come back to 24. Let me see what the other ones are. I did some of the more complicated ones. Okay, so I did 29 here in the notes on example 4. And I also did 30 as well. So maybe I'll go back and do one of these. I'll do this one. This one looks like it has a little bit of stuff going on. So I'll do 28 from the homework. And so it's just asking us to graph this using transformations. So if you're good with transformations, this shouldn't be too egregious of a problem. So another question that dawns on me is, how does it want us to input this information? So for the section, you're going to be using this exponential tool right here. And it even says at the bottom, exponential tool. Whenever I interact with the graph, it starts asking for vertical stretch, horizontal stretch, and all that stuff. So this is this gives us an idea of how to present the information. And so I'm going to move over here back to the right and sort of represent my answering all these questions. Now, the vertical stretch or compression is 1 because that's the number that's multiplied to the exponential function. The exponential function is 3 raised to the negative x. That whole thing is the exponential function. And so we don't have any number multiplying that exponential function. So really, the vertical stretch is 1. So that 3, so a common misconception students have is that they would say that 3 is the vertical stretch or compression. And that's not true, because 3 is the base, which you see at the very bottom. And notice they already put 3 for you. In some problems, they will not automatically put the base as 3 for you. In some problems, they do. And I just wanted you all to be aware of that. So here they already put that the base is 3. So that's a good, that's something good to distinguish. Horizontal stretch or compression, we never touch that. We're just looking now at vertical shift and horizontal shift. And really remember, so vertical shift and horizontal shift come down to what's adding or subtracting some aspect of the function. And all we see is a subtraction of 5. There's a subtraction of 5. And if we can figure out what that does, then we're pretty much done. So hopefully you remember that minus 5 on the outside, so subtracting the function as a whole, means we go down 5. So we need to go to our graph here. And it's really easy to determine because as you move the slider, you can see the graph over here move up and down in relation. So we just want to make sure we choose a graph that goes down 5. And so that's, and there's one more thing before I jump the gun here. There's also a reflection that I haven't addressed yet. So we went down 5, which corresponded to a vertical shift. So the vertical shift is technically negative 5. And there's also a reflection because there's a negative x, which automatically corresponds to a reflection. So the negative is on the x, which means it's a reflection about the y-axis. So this is important to determine. So we can just simply select reflect over the y-axis. And that would be our final result. And then from here, we can figure out the domain, range, horizontal asymptote, and y-intercept, which are fairly easy to determine based off of the graph here. So since we see the graph as such, we can see that the domain is all real numbers, which is always true for exponential functions. The domain is always all real numbers. The range, though, is not all real numbers because the graph doesn't go up and down both ways forever. It goes up forever. So if anything, we can expect positive infinity upwards, but downwards, we have to observe that there is a horizontal asymptote at what seems to be negative 5. And this also makes sense because we shifted down 5, and exponential functions already have a horizontal asymptote. So if we shifted down 5, the horizontal asymptote also shifts down 5. So that's why we have this particular function here. I would type these in, but typing on this tablet's a nightmare. So hopefully you can take my word from it here. The horizontal asymptote, they will end up asking for that next. And the horizontal asymptote as I just mentioned, that's what restricts our range. So it's going to be y is equal to -5. And notice I'm using an equation here. It's an equation. Y is equal to -5. And finally, we can look at the y-intercept, which all we have to do is just look at the graph and determine that. The y-intercept, it's 0, -4. Or they just might ask for the integer, and you would just put -4. But that would conclude this problem. Okay, I'll keep going. So again, I talked about this problem and this problem in my video. So I'm just going to go ahead and skip those and look at more of the algebraic problems. And I'll just do this one as a quick warm-up. This one doesn't take too long. So number 31 here. So now we're incorporating exponential equations or expressions into equations and seeing, can we still solve for x? And we can still solve for x, but we need to change the way in which we solve for x, because exponential functions, well, how do you really reverse or how do you rewrite an exponential function? And in this section, well, you're going to find out, or if you haven't already, you will find out stuff about logarithms, which are used to cancel out exponents. But in this section, we're going to try a different strategy that works for certain types of problems, such as the ones you will see throughout this section. And so this is when you want to get a common base between two expressions. So over here, I see 4 to the negative x is equal to 256. And I wanted us to find a common base, because once you can get a common base on both sides, it turns out that the bases themselves will cancel out and the exponents will drop down. So in other words, so let me grab my calculator right fast. Okay, so 256, I would love to write 256 with a base of 4. And what I mean by that is it true that 256 is equal to 4 raised to a certain power? Well, I'm just going to grab the calculator. I'm going to type in certain powers of 4. So 4 raised to the second power is 16. Okay, not good enough. Well, 4 raised to the third power, that's 64. Still not good enough. 4 to the fourth power, 256. Got it. So I'm going to rewrite this problem, not 256, but I'm going to write it as 4 raised to the fourth power. And the reason why I do that is, now notice the base on both sides of the equal sign is the same. That's exactly why I chose that specific exponent, because 4 raised to the fourth power is 256. And so now, as I mentioned, these bases cancel. And what drops down? It's the exponents. Negative x is equal to 4, or in other words, x is -4. So I just wanted to motivate that process, and we'll be seeing that with a few problems throughout. So that would be -4. And that was problem 31, by the way. This is That was problem 31. Okay. So I did talk about 32 here. I talked about this in example 5, problem, well, really it should be called problem 3, part 3. But yeah, you should notice a problem very similar to this one in the notes on example 5. So I'm going to skip that one. This one's very similar to the one we just did. Now that we already talked about this, we can probably knock out 33 really quickly. So it would be great if we had the same base on both sides. So we ask ourselves, can we rewrite 16 as 4 raised to a power? And so if you started going through powers of 4, 4 to the second power is 16. And as you can hear, they're doing construction next door. So that's going to be fun. So we can cancel out these bases. 2x plus 1 is equal to 2. And we can solve pretty easily for x. So we get that x is a half. So that's 33. So that's kind of the more complex ones I ended up doing in the video. So I did not do this one. I think this is a good one to look at, actually. So I'll talk about 34 here. So I think this one's a little bit more complex. 34 here from the homework. Okay, so 34, 2 raised to the x squared minus 35 is equal to 4 raised to the x. And so it's the same idea as before. We would love to get a common base, but we need so we need to rewrite one of these two. And frankly, we can't make numbers go up, so we can't really make the 2 become a 4. So we want to turn that 4 on the right into some power of 2. We want to simplify it to lowest terms because that's easier to write. And so how can we write 4 as a power of 2? Well, 4 is simply just 2 squared. So let's go ahead and write that down. So 4, so instead of 4 raised to the x, it's 2 squared raised to the x. So notice 2 squared is still 4, so that's perfectly fine. But now we have a common base, but we do not cancel out yet because we have an exponent raised to an exponent. And so hopefully you remember that when you have an exponent raised to an exponent like this, it's going to be 2, you multiply the exponents, in other words. So it's 2 raised to the 2 times x, just like that. And from here, now we can see that the exponents do, in fact, or the bases, rather, cancel. Oops, sorry. So that's x squared minus 35 is equal to 2x. And you might notice that's a quadratic. So we have to solve this quadratic right fast. So minus 7x plus 5 is equal to 0. X is equal to 7 and negative 5. So those would be our two answers here. Okay, cool. So 7 and -5 for this problem. So I talk about this problem in example 5. I just use 49 and 7 instead of 36 and 6. So I'm going to skip that one. So there's also, and I talk about this in my video, there's also E that they use a lot. And what E is a number. E is just like pi. But E is an irrational number, and it comes up a lot. It's a very important symbol, but we treat it as if it were a number. It's not a variable. E is not a variable. It's a number. We treat it as if it's a constant. And so for a problem like this, and I talk about a more complex one, maybe it's the next problem. Yeah, so I talk about 37 in my notes. You might already see how to do 36, but just in case. So this is 36. E to the x is equal to e to the 9x plus 72. So E, you treat it just like a number. It's not a variable. So in this case, this problem is actually really easy because the e's cancel. And then you're left with x is equal to 9x plus 72. And you can solve pretty quickly from here. It's 8x is equal to -72. What is that, just -9? So we treat E just like it were a number. So E can get canceled out. E can be moved around. It can be manipulated in all these ways, just like a number can. It's not a variable. And as I mentioned, I already did 37. $38. This one tends to trip up people a bit. So let me talk about 38. So they tell us that 7 raised to the x is equal to 4. And then they want us to determine what 7 raised to the -2x is. And so this one's kind of an odd problem because if you try to solve for x in the original statement, 7 raised to the x is equal to 4, well, you're not going to find a common base among 7 and 4. So you can't really do that cancellation thing. So the question is, how do you manipulate this problem, the statement that they give us, to where 7 raised to the x becomes 7 raised to the -2x? So how do you turn 7 raised to the x into now having that -2 in the exponent? How does that happen? And so how that happens, so 7 raised to the x is equal to 4. We need to raise both sides to the -2 power. So we raise both sides to the -2 power. And so, and in fact, what I'm going to do, oops. So I'm just gonna have to rewrite it. I'm still trying to learn this tablet thing. 7x is equal to 4. 7 to the negative 2x is equal to blank. So what I had before is you have to raise both sides to the negative 2 power. Because on the left-hand side, well, what happens is when you have an exponent raised to an exponent, the exponents cancel, or not cancel, sorry, they multiply. They multiply together, which would be 7 to the negative 2x, which is exactly the form that we want. Now, what happens on the other side? We have 4 to the negative 2. So what's 4 to the negative 2? If you put that in your calculator, you should get, what's this, 0.0625. But if you convert that to a fraction, then you get 1 over 16. And so that's your answer. So it's just seeing if you know how to manipulate both sides. So that would be your answer, 1 over 16. Because it also says type in an integer or a simplified fraction. Okay. So let's move on to the one I did. So I did 40. Okay. So I did 40 in my notes for example 6. So I'll do 39 here. And I'll just be safe and open this on a new page. So working from home, it's great. So we have a graph over here, and we're supposed to figure out the exponential function. It turns out that this problem is actually very similar to the problem that we did that had the table of values, if you remember that one. So it is the exact same problem, actually. And so in particular, what that problem had was it had an X and a Y, and then it gave all the ordered pairs. It's giving that same information as well, but it's just giving it to us with an illustration. So it's even more helpful. So we've already done this problem before. It just is giving us the information in a different way. So you might remember this from, this is example 2 from the notes. We did this exact same problem, and we're trying to figure out what the exponential function is, which every exponential function takes on the form in one way or another, a times b raised to the x. And so what we did for example 1 was we went ahead and plugged in the point, well, really the y-intercept. Because when we do that, so we have a test point of 0, 1. So now it says that 1 is equal to a times b raised to the 0 power. But b to the 0 power is just 1. So really it just says that a is 1. And now we can take our original function and replace a with 1. So now we simplify it a little bit more, and we just get b to the x. Or in other words, our vertical stretch is just 1. But we still need to figure out what b is. And so we pick another test point. And so and also, I do want to give this disclaimer. because I made the same mistake the last time I taught this. The disclaimer is the reason why I chose, so I think this is a little important. The reason why I chose f of x is equal to a times b of x is because I noticed that this function has the same exact shape as the parent function. It has the same exact shape. However, if I were to look at problem, what was it, 40? If I looked at problem 40, I would not use that shape. Instead, I would have to realize that this is a reflection about the x-axis, which means you might need to consider a negative sign in front. No, I think in this problem, it actually works out that way for you. You will end up figuring out that a is a negative number and it goes from there. But if you had a problem where you reflected about the y-axis, you would have to put the negative on the x yourself. That won't just come up naturally. So I did want to give that sort of disclaimer. But if anything, that's just a small footnote. So I think it ends up working out nicely in this problem here. I'll probably talk about it in the video as well. But let me get back to the other problem. I haven't finished it yet. So like I said, we need to pick another test point to figure out what the value b is. Oh, okay, that was weird. 1 second. All right, cool. So we pick another test point so we can figure out what b is. So 7 is now equal to b to the first power, which means that b is 7. So the function itself is 7 raised to the x. And that would be your final answer, just 7 raised to the x. Okay. And so again, I did 40 in class or in that lecture video for example 6. So I'm going to skip it. Okay. We'll come back to that one. 42. So really, there's only 2 more problems to do, 41 and 42, because 43 and 44 are the last 2 problems I do in the video. So I'll do 41, 42, and that'll conclude every problem from the homework. Okay, so 41. And they tell us that g of x is equal to 3 to the x plus 3. And then they start off by asking us something fairly simple. What's g of negative 1? So g of negative 1, we simply plug in negative 1 for x. And so if you were to plug this in your calculator, 3 raised to the negative 1 plus 3, you get 3.333. If you convert that to an improper fraction, because you have to provide your answer as a fraction, it's 10 over 3. And then they go on to say, what's the point on the graph that this corresponds to? The point is you plugged in negative 1, and then you obtain 10 over 3. So here's the answer for that first blank. Here's the answer for the second blank. Again, these are kind of tedious to type in using this tablet, so I'm just going to state them there. Move on to part B. Because part B, what that says is, well, what happens when the function as a whole is equal to 12? What happens to x? And so what we're doing is, well, we're setting the whole function equal to 12. And we have some like terms. We can subtract 3 on both sides. So we get 3x is equal to 9. So hopefully you remember what to do in this situation, because to solve for x in an exponential, we can find a like base. And 9 can be written with a base of 3, because 9 is simply 3 squared, because 3 to the second power is 9. And so the 3's cancel. And we get that x is equal to 2. And that's it. So that would be the first blank. And then it asks for the point on the graph. And the point would be 2, 12. Because they gave us that y was 12, and we found that x is 2. So then 2, 12 for the point. So from there, there's really just one more problem that I haven't covered. And it's really not too bad of a problem, even though the wording makes it seem like a complicated problem. So this is 42. And whatever all that other wording means, I don't know, that sounds a little bit technical. I see that there's this function that's equal to 100 times 0.99 to the n. And so with this, they're saying that P is the percentage and N is the successive panes. And then for part A and B, really all they're doing is giving us the value for N. So in other words, they're giving us the X value and having us solve for Y. So this is a glorified do it in your calculator problem. And that's all it amounts to. 100 times 0.99 raised to the 15th power. And so as long as you can put all of that in your calculator, which means you need to know how to put arbitrary powers in your calculator, such as 15th power raised to the 15th. And it does say round to the nearest whole number. So I'll put 86. And then part B, it just says, well, instead of 15 that you're plugging in, plug in 35. And that's it. So this problem is really easy, actually. As long as you can plug all of this in the calculator. And again, round to the whole nearest whole number, that's just 70. So that's part A and that's part B. And that, between my lecture video and this homework review session, I've now talked about every homework question. So I don't have anything to talk about. Next Monday, or this Friday, the tutors are going to discuss the workbook page. And the next Monday, I'm going to do problems for the section on logarithms and have the homework due Monday night if I haven't already pushed it back. But so that's the plan moving forward. So if you have any questions for me, I'll stick around. If not, that's really all I have. So have a good day.